Okay, so to solve question 1, or question 1a says determine the degree and leading coefficient of the polynomial. So we know that right here, okay, sorry, so the degree is determined by the highest power of x in the expression, which we can see here is x to the power of 4. So our degree would actually be 4. And the leading coefficient is the coefficient of the term with the highest power of x. So obviously this is the highest power of x, and the term here would just be a 1. So the leading coefficient is just 1. And then, so for the next question, they ask us to find the x-intercepts. So how do we find the x-intercepts? Well, what we can do is set the equation to equal 0. And then what we do from there is find all, we can use the rational roots formula stuff to figure out like what are some possible roots, and then what we would do is input these possible roots into the formula to figure out what they would be. So what we do is we'd just do like P over Q is equal to like we start listing off some possible roots of 6 here. So some possible roots would be plus or minus 1. Oh, I should probably put the comma there. Plus or minus 2. Oh my, okay. Plus or minus 3, and plus or minus 6. And then we can divide all this by the leading coefficient, which is 1. Okay, so to save us some time, well, I know that a root is x minus 2, so let's just say we would randomly choose f at x is equal to so 2 to the power of 4 minus 7, 2 to the power of 3, what's next, and then plus 19 times 2 to the power of 2. So we're just inputting the value into our function, and it should equal 0. So then minus 21, 2 plus 6, and then, okay, so here we have 16, and then minus 56, 76, minus 42, and then plus 6, and then this equals to 0. So, oh, I should probably, this should be a 2 right here, sorry. But, so f of 2, it is a root, or a possible 0. So what we would do now is actually set up some synthetic division. And we put a 2 here, and then we put our coefficients in here. So we have 1, because there's an imaginary 1 right there. Then we have negative 7, we have 19, negative 21, and we have 6. So we bring the 1 down. 2 times 1, well, that is 2. So negative 7 plus 2, well, that's negative 5. And then we do 2 times negative 5, which is negative 10. So this would be 19 plus negative 10 is just 9. 2 times 9 is 18, which gives us negative 3. And then 2 times negative 3 is negative 6. So 6 plus negative 6 is 0. So 2 is a root, or a 0. So we can write our equation here as x minus 2, x to the power of 3 minus 5x squared plus, so we have to like lower it because we already have a fact, like we factored the x out. So plus 9x minus 3. So actually, if you try any other one of these factors, you actually find out that this can't be factored any further. So what we would do here is do like some Ralphson method of finding the derivative, and then you get an estimation of what a root could be. So to save us some time, like I did it right here, but to save us some time, I already know that x is going to equal close to 0. So we know that. And yeah, and then we also know that x is equal to 2 because we just did that right there. Okay, that was kind of long, but almost done. So the next one is to state the domain and range and evaluate the end behaviors. So since this function is a polynomial, the domain is just x is equal to all real numbers. For the range though, it's a little difficult to find the range, but if we talk about like the end behaviors, we know that it's an even degree polynomial, as you can see right there. And this term in this function will dominate the function for every positive and large values of x. So essentially what that means is that the graph of this function will always approach positive infinity. So like for an example, like it'll always look something like that. It's not going to look like that exactly, but it'll always look something like that. Yeah, so the range is a little difficult to find, but it actually is y is greater than or equal to -2. Yeah, it's greater than or equal to -2. So next was to sketch the graph. So how we would do this is that, draw a little like graph here, and well, we know what the end behaviors are, so we can just put these there. We know that we have an x-intercept close to 0 and 1 at 2. So I guess for this, you can kind of just, you can estimate. So like there's gonna be a point like somewhere there because it's close to 0. And then there's one at 1, 2, and there's gonna be one right there too. So yeah. So basically we can just draw it. It's gonna look something like that. Oh, I would put the thing through there, but because there's a multiplicity of 1 here, like there, and then it's a little hard to figure out what it would be here, but essentially your graph would look like that because we have a positive leading coefficient. And well, yeah, and that's how you do question 1.